Welcome to our channel. In today's video, we're delving into the world of data warehousing as we explore one of its fundamental schema types, the Star Schema. As the cornerstone of analytics, a well-designed data warehouse can make all the difference in achieving meaningful insights. Join us as we dive into the basic concepts of the Star Schema and uncover its significance in shaping the data landscape. In this presentation, we will define what a Star Schema is, explore its advantages and disadvantages, and then break down its essential components. We will review its benefits and drawbacks. By breaking down the core components that constitute a Star Schema, we aim to provide you with a practical example that enhances your understanding. Stay engaged as we share valuable insights into best practices and the pitfalls to avoid when working with Star Schemas. By the conclusion of this video, you will have developed a comprehensive understanding of this vital data organization technique. What is a Star Schema? The Star Schema is a type of relational database model that is commonly used in data warehousing. It's designed to optimize querying and reporting performance for analytical purposes. In a Star Schema, there is typically one central fact table that holds the quantitative and measurable data, such as sales, revenue, quantities, etc. This fact table is surrounded by multiple dimension tables, which provide context and additional descriptive attributes related to the data in the fact table. The Star Schema gets its name from the visual representation it forms, where the fact table is at the center, forming the core of the star, and the dimension tables surround it radiating outward like the arms of a star. The relationship between the fact table and dimension tables is established using foreign key relationships. Advantages of a Star Schema. Performance. I have observed numerous analytics projects fail when attempting to use databases not explicitly designed for analytical purposes. If a schema is adaptable to a specific application, it's generally unsuitable for analytics. Attempting to perform analytics on a schema not optimized for it often leads to significant performance issues. In a Star Schema, data segregation into fact and dimension tables optimizes queries for faster execution. This leads to more efficient aggregations and joins, resulting in quicker access to insights. Loading data in a Star Schema is facilitated by its simplified structure. The central fact table and dimension tables linked by foreign keys reduce complexity, necessitating fewer relationships to oversee. Furthermore, maintaining data integrity across the various tables becomes more straightforward. Maintaining referential integrity is streamlined in a Star Schema due to direct relationships between the central fact table and dimension tables. With fewer dependencies compared to normalized schemas, updates are primarily confined to dimension tables, reducing the risk of cascading changes. This focused update approach simplifies the enforcement of integrity constraints. The schema's simplicity also aids in efficient validation and accurate relationship management. Disadvantages of Star Schema. The limited scope of a Star Schema in analytic usage is a result of its optimized structure, designed for specific query types. It is fine-tuned to address a predefined set of business questions, utilizing a single unique fact table. However, this design restricts the inclusion of diverse types of entities within the same model. To encompass a broader range of scope and answer questions on various topics, a different schema becomes necessary. Star Schemas are also not well suited for handling certain types of analytics involving non-structured data. A Star Schema is rigid due to its predefined structure, optimized for specific analytical queries. Its fixed architecture doesn't easily adapt to evolving data needs or accommodate diverse data types. Changes require altering the schema, potentially affecting existing queries. This rigidity contrasts with more flexible models that allow for dynamic adjustments and broader data variations. Maintaining data integrity in a Star Schema requires high-quality data. Since the schema relies on clear relationships between the central fact table and dimension tables, inaccuracies or inconsistencies in data can affect the reliability of analysis and reporting. High-quality data ensures that the relationships remain accurate, which is crucial for producing meaningful insights from the schema. Star Schema components. The fact table is the central component of a Star Schema, holding data that is subject to analysis, reporting, and calculations. Typically, it includes key performance indicators at the necessary level of detail. It also contains foreign keys that establish connections with various dimension tables, enabling comprehensive insights through data relationships. Dimension tables typically contain descriptive information and provide a means to filter, categorize, and provide context for the data stored in the fact table. Now that we have the basics, let's take an example and visualize how the star schema would appear. A company wants to analyze its monthly sales data. For each month, they provide the transaction date, product details, sales, and taxes. In addition to analyzing the data, it's crucial to have the capability to filter items by type. Furthermore, the system should display the name and description of each item, along with the ability to filter by item category. Before beginning the exercise, a few comments on common mistakes that frequently arise during the design process. It's essential to consistently construct your schema in alignment with the requirements rather than the existing data. To take it a step further, it's advisable to refrain from even examining the data initially. Instead, devise the complete schema based on the specific question you aim to address. This approach will aid in avoiding any potential bias from the data's existing format and result in a more versatile and business-focused schema. I typically begin by establishing the fact table. In our scenario, we are working with two quantities that require utilization, the sales amount and the tax amount. Once this step is completed, I introduce the necessary foreign keys to establish connections between the fact table and the forthcoming dimension tables. In our example, we will employ two dimension tables, one for time and another for products. It's worth noting that the time dimension table exclusively encompasses years and months. This choice stems from the problem's specification, indicating a requirement for monthly analysis. Consequently, the fact table will operate at the monthly level, the most detailed level required. In the event that the data arrives at a transactional level, a pre-processing step to aggregate the data into a monthly format would be necessary prior to integrating it into the schema. Within the product dimension table, you will discover fields for the name, description, and type. The name and description serve the purpose of showcasing the outcomes. Meanwhile, the type holds the potential not only for display purposes but also for functioning as a filter or a parameter for grouping during the analysis process. With this very simple schema, you can start generating different types of output via any analytics tools. I usually used Power BI, but Tableau, C-Sense, etc. are all good tools. In this example, I am just using an Excel's file to illustrate a few examples. In this first example, I used the type from the product dimension table to summarize sales and taxes. Summarized data are often the starting point of a lot of analysis. I can also summarize data using the time dimension table and showing total per month and year. As previously mentioned, one of the main role of dimension tables is to perform easy grouping. Following the same logic, I could use the item in the description from the product dimension table and perform another grouping. Dimension tables can be used to filter the dashboard. In that case, I am using field from time and product dimensions. Ideally, you should never use fields from the fact table to filter. Finally, I could use the lowest level of data from the fact table combines with the dimensions table to generate list. This can be used for drill-down functionalities or list. Now, let's consider the scenario where we aim to carry out a similar analysis focusing on store-specific data. In this situation, it becomes necessary to introduce a new foreign key within the fact table. Additionally, an extra dimension table would be created to incorporate the indispensable store-related information. It's important to note that the number of dimensions within a star schema has an almost boundless potential, mirroring the count of fields present within a fact table. The inherent simplicity of the schema plays a significant role in this aspect, resulting in the total number of fields and rows within the fact table having a minimal impact on the overall query performance. Now that we have grasped the fundamental concepts, let's delve into several aspects you should avoid when working with your star schema. The illustrations I provided are derived from my personal experience. While certain instances might appear trivial, they frequently arise due to evolving requirements, where developers attempt to adjust swiftly, inadvertently veering away from the rigorous principles of the Star Schema. Regrettably, more often than not, the consequences of such actions become apparent later on. The first one is obvious but unfortunately frequent. In a Star Schema, cat should be called a cat, meaning that the name of the field or the table should reflect the business meaning of the field so anybody can understand without a database dictionary. Inconsistent conventions. Maintain consistent naming conventions for fields and tables throughout your schema. Inconsistencies can lead to confusion and hinder collaboration among team members. Complex hierarchies. Keep hierarchies and dimensions straightforward. Avoid creating overly complex or deeply nested hierarchies, as they can complicate queries and impact performance. Bypassing dimensions. Never directly filter or group from the fact table. Always use dimensions for filtering and grouping to ensure accurate and efficient query results. In conclusion, a successful Star Schema hinges on two core principles. First and foremost, it must remain laser-focused on addressing the business needs at hand. This ensures that the schema's design aligns seamlessly with the analysis objectives. Equally important is maintaining clarity and simplicity while adhering to the fundamental tenets of a Star Schema. By embracing these principles, your Star Schema becomes a powerful tool for extracting meaningful insights from complex data structures. Thank you for watching this video, and I greatly appreciate your feedback and insights. In upcoming videos, we'll delve into different schema types. If you're eager for more valuable content, consider subscribing and liking the video.